So segment 4, we've been working towards being able to draw our Lewis structures. We had looked at polarity. We looked at how to make a moment out of that based on distance and charge. We talked about delta partial charges. And so now what we're going to do is start to put all that together to make drawings. So we're going to find these are very useful because it's a way of diagramming the structure, what it's going to look like in 3 dimensions. We can use this to make reasonably accurate predictions about its shape. And so the first thing we're going to say is not all of the molecules are going to obey the octet rule, but for the ones that are in the group 1A through 8A, these will work out pretty well most of the time. Boron and beryllium will sometimes have less than an octet. Once we get to the second row, we can never have more than 8 electrons. However, once we get to the third, we'll start to see we can exceed that octet. And of course, we're going to discuss why. Just to let the cat out of the bag real quick, or you might even already know, is once we get to those d orbitals, all right, then when n equals 3, that third row, the shell can now have up to 18 electrons. So once we introduce that third energy level, even though typically we're looking at s and p electrons, that d orbital is there. And even though that we fill the 4s before we fill the 3d, that 3d is there. So once we introduce that third energy level, we have all 18 areas or spots that can be occupied by electrons, right? So that's going to lead to an excess, potentially, of the octet rule. All right, so the method for drawing Lewis structures then, what we're going to do is we're going to decide how our atoms are going to be bonded. So we're going to look at skeletal structure, and we're going to look at the arrangement of the atoms. We'll start off with a term called the central atom. Typically, the central atom is written first, and then after that, it's also going to be the least electronegative. And then we're going to see that everybody else is going to connect to that central atom. So like Grand Central Station, you know, if you've ever been to Grand Central Station in New York, you can grab a subway, a cab, a bus. So you have all these different modes of transportation all in one place. Same thing with the central atom. It simply means that everything else is going to connect to it. It's like that central hub, if you will. What we'll do next is count all of your valence electrons. Okay, so we'll figure out how many total electrons we have from all of our atoms. And then, of course, we're going to place 2 electrons between each pair of atoms. So we're going to draw in single bonds right away, so everybody's connected. After that, we'll complete all the octets of all the terminal atoms. So, of course, that's all the atoms attached to the central atom by adding in the pairs of electrons. Any remaining electrons we'll then put on the central atom. Now, at this point, if the central atom does not have an octet, we're going to have to start looking at how we're going to form double, possibly even triple bonds. Okay, so let's give it a shot. We'll do an example, SiF4, so silicon tetrafluoride. And so the first thing we're going to do is figure out how many electrons do we have. So we have 1 silicon. It's got 4 valence electrons. Then we have 4 fluorines. Each one has 7 valence electrons. Multiply that out, that gives us 28. Now we'll sum that total up, and that's going to give us 32. So we have a total of 32 electrons for our entire structure. So the first thing we'll do is put the central atom, silicon, which we've written first, right in the center. We'll draw in 1 pair to each of the fluorines. Okay, so at this point, everybody's connected. The next thing we'll do is we'll subtract that out. How many electrons did we use for our single bonds? Well, we used 4 single bonds, 2 electrons each, total of 8 valence electrons, which means we have 24 left over. The next thing we'll do is complete our octet. We'll fill in all the electrons around each one of these outside atoms. So fluorine, then we got 2 from the bond. We'll add 2, 4, 6 more. That gives me a total of 8. Complete that octet. And we'll do that for all the rest. That's going to use up 24 electrons for each one of those lone pairs, which gives us 0 electrons left over. And of course, the last thing we'll do is for silicon, we've got 2, 4, 6, 8 with the 4 bonds. So silicon's good. All 4 of the fluorines are good. So that means we should have a pretty decent structure there. All right. Another example, H₂CO3. Remember that the carbonate is an oxoanion. So within that polyatomic, the C is the central atom, and the oxygens have to surround the carbon. The two H pluses then will be attached to two of the oxygens. So the first thing we'll do is we'll get our total of electrons. So we have one carbon with 4 valence electrons. We have 3 oxygens, 6 each, that's a total of 18. The 2 hydrogens each have 1, so we'll add another 2 in. Summing those up, we have 24 electrons total. So the first thing we'll do is draw in single bonds. So we'll take our carbon, it's central, so we connect all 3 oxygens to it with single bonds. And then for 2 of the oxygens, we're going to connect the hydrogens. So there's our single bond skeleton, right? And so we've used up 1, 2, 3, 4, 5 single bonds. So that's going to be a total of 10 electrons, which means we have 14 left over. So the next thing we'll do then is add electrons to the oxygens to get their total octet up. And so for this oxygen, we'll add 2, 4. It's already got 4 from the bonding. This one, same thing, 2, 4. It already has 4 from the bonding. The one on top here, however, we'll do 2, 4, 6 to make that a total of 8 with the single bond. That uses up all 14 electrons. Now, if we look at our central atom, the carbon, we'll notice that the carbon only has 6 electrons at this point. So we know that's too few. Carbon's going to need an octet. So the only way we're going to get that is to convert one of the lone pairs on the oxygen to a second bond to the carbon. So again, we'll start with this structure, but now we're going to take one of these lone pairs and push it in to the bonding area. We'll form a double bond that way, and we'll end up with the final structure CHO3, where we have a double bond with the oxygen, 2 single bonds, and then our H₂ will be on those 2 single oxygens. Now, another way you can do this, another method for doing electrons, is to look at the halves and the ones. So we do the halves in this method. So we know that when we did that, if we flip back, we had 24 electrons. So we have, right here, we have 24 electrons. The next thing we do is look at our wants. Now, what we want is for everybody to fill their octet. Hydrogen will be different where it only wants 2. But everybody else is going to want 8. So we have carbon and oxygen, but we have 3 oxygens. So that's going to be 4 atoms that want 8 electrons. So 4 times 8 gives me 32. Plus the hydrogens each want 2. So that's going to be 2, 4 added to that. So that's going to be, add 4. That's going to be 36. So to make everybody happy, we want 36 electrons. Now what we can do is find that difference. So that's going to be 12. 12 electrons. Right? And now we're going to divide that by 2. That's going to give us 6. Now the reason why we're dividing by 2 is this is going to be 2 electrons per bond, which means this is going to be 6 bonds. Okay, now we know we're going to need 6 bonds, so I'm going to start out the same way. I'm going to have carbon as the central, and I'm going to connect the 3 oxygens. That used up 1, 2, 3 bonds. We know the hydrogens are going to connect to the oxygen. So we've used up 2 more bonds. That's now 5 bonds. But this told me I'm going to use 6. So I need to draw in another bond. Well, at this point, oxygen doesn't have any bonding electrons left. Oxygen doesn't have any bonding electrons left. Carbon still needs to use up 1. This oxygen still has 1 more. So we're going to put our 6th bond right there. So the method is pretty much the same. It's just working from the bonds rather than the electrons. Now we'll put in electrons to make everybody happy. And then you would count up all your electrons to make sure that you didn't go over how many you have, which is the 24. All right, so either one of these methods will work. They're both tools to get you to the correct structure. All right, so our next compound is going to be N₂F₂. So nitrogen has 5 valence electrons. That gives us 10 for nitrogen. we have 2 fluorine, 7 each. That's 14. Again, another total of 24 electrons. So we'll start out with a skeletal structure where everybody's connected with a single bond. We've got 3 bonds. That's going to take away 6 of our electrons, leaving us with 18. We'll then fill out the octets on the terminal atoms. So now we're going to use 12 more. That leaves us 6 electrons left. We'll take 3 of those and put them around one nitrogen, 3 around the other. And of course, that means we do not have complete octets. Here we can see we now have 7 around the nitrogens, right? But that gives us 0 electrons. So again, here we're working from the electron point of view. Now we're going to make the electrons work. We can see we don't have enough to complete the octets of the nitrogen, and so we're going to form a double bond. Each one of those nitrogens is going to push one single electron in, and that's going to give us a double bond between the 2 nitrogens. Now, elements after period 2 in the periodic table are usually larger atoms and have your d orbitals as well, which means you can have up to 18 electrons in that total shell. So for Lewis structures, we're going to follow all the same process as before, but any extra electrons will add to the central atom. So for instance, let's take a look at PCl5. Same process. We have phosphorus, 5 electrons, one of them, 5 chlorines, 7 electrons each, 35, gives us a total of 40 electrons. We know that the phosphorus has to be the central atom. Now this is a little weird, but we're going to put all 5 chlorines connected to the phosphorus. Give you a second to digest that. All 5 chlorines are going to be connected to the phosphorus. Now, one way you can think about this is chlorine is a terminal atom. Chlorine is only going to make a single bond in most normal instances, which means none of them can be in the middle. So we can't have phosphorus, chlorine, chlorine. That won't work, right? The chlorine in the middle there would be overextended with its electrons, and that doesn't happen. Not very often anyway, only in special circumstances. So that means we're going to connect all single bonds to the phosphorus. We use up 10 electrons this way, we have 30 left over. Now we're going to fill the octets of all the chlorines. That's going to be 6 of them on all 5, means we use up all of our electrons. So the phosphorus at this point has 10 electrons. That's a little strange, but since it's in the 3rd period, we're going to say, okay, it can expand its shell, and that's going to have to be the correct structure. Now remember, these models are representing the best idea. None of them are going to be perfect. There's going to be some other concepts we're going to look at as we move through bonding that's going to help to make sense of some of these structures. Now, you can also have electron deficiency. We'll see this with boron quite a bit. Boron often has 6 electrons around it, so it only ends up with 3 pairs. Beryllium, is also going to be a little shy there, where it's only going to have 2 pairs. Now beryllium, though, that kind of makes sense because beryllium is in group 2A. We actually expect it to give its electrons away. So the fact that it just behaves in covalent bonding makes it already an exception. All right. Let's take a look at boron tribromide here. So we have 1 boron with 3 electrons, 3 bromines, 21 electrons. We draw out our basic structure with our 24 electron total. We're going to use up 6 in bonding. That leaves us 18. We're now going to go ahead and complete those terminal bromines, and that's going to use up all 18 electrons. So boron here only has 6 electrons, and it will not form a double bond. So it's just going to end up with an incomplete octet. Okay, so for boron, that's going to be okay. Now, how many electrons does NO2 have, and how many are in the structure below? So how many electrons does NO2 have, and how many are in the structure below? So for NO2, we know we have 5 valence electrons for the nitrogen, 6 for each oxygen. So that's going to be a total of 17 electrons. In the sterolene, we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So our answer should be B, 17, 18. All right, what type of bond exists between carbon and oxygen atoms in CH2O? i.e. is it single, double, triple, etc. So between C and O, it's a single bond, a double bond, a triple bond, or there is no bond between the carbon and the oxygen because the oxygen is bonded to a hydrogen. In other words, it goes CHO. If you pick D, I will not be happy with you. Right? Because we know that hydrogen only has one electron and can only accept one electron because it's in group 1A and it's in the first period. It only needs 2 electrons to complete its octet. And so it can't receive a third electron. That means there's no way hydrogen here could be in the middle with 4 electrons. It's just can't happen. So D cannot happen. Okay. So is it a single, a double, or a triple? If we look at our electron count, we have 4, 5, 6. We have 12 electrons total. We'll make single bonds to everybody. We know carbon's going to be in the center. We've used up 6 electrons, which means we have 6 left over. So we've completed all the octets except for carbon, right? Because that's going to use up the 6 electrons on the oxygen. So we have no electrons left over, which means we're going to take 2 of these, put them in here to make a double bond. So again, our answer will be B. All right. If more than one Lewis structure can be drawn, which one is going to be correct? Now, the experiment will always decide this. Concepts such as formal charge and resonance will help us to make predictions. So 2 new concepts to us will be the formal charge and, of course, resonance. Now, again, you might have seen electron dot structures in a lower level of chem or even in your high school chem, and maybe you've seen resonance or have an idea of what resonance structures are, but typically formal charge will be new to us. Formal charge is pretty simple. Once you see it done in action, it's not going to be too bad. It's probably going to be on the next segment. We're going to run into our issues with our next compound, and we'll leave that as our cliffhanger, and then the next segment we'll look at how we're going to take care of that. So H₂SO4 is our next example. So if we run through this really fast, we know that we have 1 sulfur for 6 electrons. We have 4 oxygens, 6 electrons each, that's 24. 2 hydrogens, 1 each, that's 2. We sum that up, we get 32. We're going to put in all of our single bonds. Now, again, SO4 is a polyatomic, so we know that the sulfur is going to be the central atom there. So each one of those oxygens will connect to the sulfur. And then we're going to connect hydrogens to 2 of the oxygens. Here we decided to put it this way simply to be symmetrical. We'll find in nature things are typically going to be symmetrical, and so that makes sense for us from the chemistry point of view. We look at our bonds, we have 2, 4, 6, 8, 10, 12 electrons are used up for single bonds. That leaves us 20. We'll then put in lone pairs on all the oxygens, and that leaves us with 0 electrons. Now at this point, everybody seems to be happy though, right? We have hydrogen with 2, oxygen with 8, oxygen with 8, oxygen with 8, sulfur with 8, oxygen with 8, and hydrogen with 2. Now, since our n equals 3 for the sulfur, we know we have n empty d orbital. Now we could expand its octet, so we could write the structure with double bonds. So here we could take this pair, stick it here, and this pair, and stick it there. So we have 2 potential structures here. So how do we know which one is going to be accurate? All right, and that's what we're going to pick up with in our next segment. So we're going to stop here. We're going to leave you with that little cliffhanger of which one of these structures is going to be the accurate structure. All right, stay tuned.